I forgot. I'm sorry. Just bend it over, like this side. Okay, that works too. Okay. So I think last time we agreed that the southwest position on this one was the most likely, if I can remember. So let's sort of defend that answer. So what we should do is go through each group individually and see where it's going to direct an incoming substituent. So we'll do the OH group first. On our chart, which I should have handy. On our chart, the OH group is up here with the activating groups. And so that means it's a fairly strong orthopara director. So that means, oh my god, HO, H3, NO2. So the para position has the nitro group, so that's blocked. And then the ortho positions are here. That one's got a methyl group. And then that position's open, so the OH is going to direct strongly to that position. Okay, next we'll do the methyl group. So the methyl group is basically R. And that's a fairly weak activating group, so that's a weak orthopara director. Okay, so the ortho positions are here. So this position will be weakly directed towards. And then the para position is here, and so that position will be weakly directed towards. And finally, the nitro group. Nitro is way down there at the bottom, strongly deactivating groups. And so that's a strong meta director. And the meta positions from the nitro group are where the methyl group is, and then that position as well. So there is some competition, but it's not very good competition, is it? Because both of our strongly directing groups are pointing toward the exact same place, and then we have some minor favoritism toward these other two places. And so it's going to be this southwest position right there that gets substituted. And so it doesn't matter what reaction we do. We could do a bromination, we could do a nitration, or any of those. It's always going to direct to that same position. Okay. So we've just talked about electronic effects so far. This ortho para meta directing business That's all related to the electronics and the resonance structures and all that stuff. But there is a steric component to this. It's not nearly as important. But if you have something like that, a tert-butyl group, which is about as sterically large as you can get because you've got tons of stuff on that benzylic carbon right there. In addition, this being an R group is an ortho-para-director. And so because of those two things, para is going to take at least some precedence over ortho when you have a large group like this. So if we do a nitration, we can make the ortho product. Or the para product, and this is probably going to be the major product because this bulky group here is kind of blocking the ortho positions, and so it's harder for that nitro group to get in there and react, whereas the para position way on the other side of the molecule is relatively more free. Okay, so we have a similar effect where we have a para-substituted ring. Di-substituted, really. And we're generally going to go ortho to the small group. This will make sense once you see it. So if we've got a tert-butyl group on one side and a methyl group on the other side, these are both ortho-para directors. In this case, the para doesn't matter because the para position is blocked in both cases. But the methyl group is going to direct to the ortho positions next to it, and the tert-butyl group is going to direct to the ortho positions next to it. And so assuming that they have the same amount of directing power, which they basically do, then we can look at the sterics and say, okay, these two positions are slightly more sterically hindered because of the tert-butyl group next to them versus the positions that are ortho to the methyl group. So we have the option to do that. Or do that. And so the more favorable or the major product is going to be that one, where the nitro group is ortho to the methyl rather than ortho to the tert-butyl. And then finally, for meta-substituted rings, that middle position in between the two groups that are meta to each other are disfavored. So instead of this para arrangement here, if we had this type of thing, right? I think we can see that this position here is sort of in the middle of all that business. And so, you know, if we're comparing this group, which is ortho to both of them, versus these two positions down here, which is ortho to one and para to the other, ortho to one and para to the other, this position is somewhat sterically hindered. So we could put it there, or there, or there. Those are our three options. This one, because it's, well, first of all, it's right next to the tert-butyl group, and it's between the tert-butyl group and the methyl group, so we're going to get essentially 0% of that. And then we've got to decide between these two. Well, we already said that we're going to favor being ortho to the smaller group, the methyl group. And so that means that this is going to be major product, and that one will form in somewhat smaller amount. So those don't come into play super often. Usually you're going to find that the identity of the groups, whether they're ortho-para-directing or meta-directing, is going to have a greater effect on where things end up going. And this will only be the case if you have two similar groups like this, where they're both essentially alkyl groups. And now, okay, now we have to compete between those two to figure out where things are going to go. All right. Okay, we're going to talk about the S word that I know you guys don't like. Dun dun dun. Synthesis. Okay. So synthesis shouldn't be as scary as it is. And the thing that people get like worried about in synthesis is the individual reactions themselves. So if you have at least a fairly good grasp on the reactions that you're going to end up using in a synthesis, then it makes it a little bit easier. You still have to do some, critical thinking and such, but I think at least when you're starting to work on these problems, so what is it, number 5 on the homework? Yeah. Just have like a list of all of those reactions, all of the reactions we talked about in front of you, and then go from there. So let's say that I'm asking you to go from benzene to that molecule. So we're going to have to do 2 EAS reactions in order to get the groups onto the benzene ring. The question is, what do we do first? Do we install the nitro group first, or do we install the alkyl group first? Any gut feelings? Yeah.
So the thing on the right, the alkyl group, I feel like that should go first because the NO2 likes to attach to the meta position, right?
So the NO2 likes to direct other groups to the meta position.
Yeah. So opposite.
So the opposite. Yeah. So if I'm going to do the wrong answer first. I'm going to do it in red. So let's say, okay, let's install the alkyl group first. So I'm going to do that alkyl halide and FeBr3. Okay, so this is a valid reaction. That'll work. Now we need to do a nitration. So we'll do our nitration reagents. But the problem here is we're going to get para and ortho. So that is not the order that we want to go in. Instead, let's do the nitration first. And now, when we go to add do our Friedel-Crafts alkylation, the nitro group is going to direct to the meta position. And so we're going to get the meta isomer. Okay. That looks very similar, but it's actually significantly more tricky. Okay? So take a moment and think about how you might synthesize that one. Okay. Some hints and clues. How do we install that NH2 group? So in order to get an NH2, we have to first install a nitro group and then reduce the nitro group to the amine. What about the alkyl group? Can we use this 1, 2, 3 carbon chain with a bromine on it and do an alkylation? No, why not? Let me draw that up. It's time for some red pen again. Okay, so well, actually, I'll split this into two parts. The first part is this. So this will be part A. All right. So in order to do that, we have to do a nitration. And then we have to reduce the nitro group to an amine. And that's the reagents we use for that reaction. Okay, so that's how we get an amine. Okay, let's switch gears and talk about B. Okay, so if we say, all right, I'm going to do a Friedel-Crafts alkylation, what will the product of that reaction be? Oh. So remember carbocation rearrangements? Yeah. So we're going to, at some point, end up with that carbocation, which is going to rearrange to that carbocation, which is going to give an isopropyl group. So the way to get around that is to do an acylation because when we do an acylation, there's no rearrangement. And then we have to reduce the ketone to just the alkane. Yes?
The only reason why you do is a psyllium ion, right?
Is what?
A psyllium ion?
Yes. Yeah.
The only reason why you do that is so you don't have to rearrange it, right? Because if you were just to do the same thing with the chlorine, you get the same product.
Do the same thing with what?
So if you were just to do another, I don't know.
Okay. Okay, so we have ways to do both functional groups independently of each other. But we need both of them on the molecule. So so they're para to each other. right? And so that means that we need one of them to be a orthopara-directing group when the other group is put on for the first time. So we've got, so I'm going to pretend that these two groups are, that all these groups are on the same molecule, but so an amine is an orthopara-director. The alkyl group is an orthopara-director. This ketone, what is that? It's a meta-director. And the nitro group, hopefully you remember, is also a meta-director. So that means that what we couldn't do is first start with benzene, do a nitration to put the nitro group on, and then immediately go and do our acylation, because then this is a meta-directing group, so then we'll end up with the acyl group in a meta position. So what we'll have to do is go all the way to the end on this one. So we will take so we'll take aniline. So that's an orthopara-director. And now to that we will add our Friedel-Crafts acylation. And then to get to the final product, we do the reduction of the ketone. And that gets us to the final product. Questions on that? This is on the more difficult end of the scale, and the one we did up here is on the easy end of the scale. Yes?
Whenever you split them up into two different reactions,
Yeah.
why could we have done the second one first?
Absolutely.
If the final product wasn't. So we could have done right away.
Yep, so you could go, okay, all right, do the nitration here. And then, sorry, there we go. Yes. And that's kind of the blessing and the curse of synthesis problems, is there's almost always multiple correct answers. Okay. Let's do C. So for these synthesis problems, you don't have to show mechanisms. You don't have to show any intermediates or resonance structures or anything. You just need the starting material, an arrow that shows the reagents and then going to the next step and do that however many times you need to get to the product. Another recommendation, make sure you don't just try to pull the chemical reactions out of your ass. Have your notes as reference, because what I really want you to practice here is the thought process of doing the synthesis. I'm not trying to like rack your brain on remembering all of the different reagents. That will come as you continue to do this. Yes.
So I feel like I would start with
Okay, you can start with either one, actually, it doesn't matter.
But I haven't had the chance to watch the returns on Friday. So to add in with you to, I had a random guess that it was
It's just like this first reaction you did for bromine, but
that's what I, okay, that was
Yep.
my guess. Okay. So, thank you.
yes. So it's the weird second. Where it's a deactivation, but it's going which is good for us.
Bro. No, it's okay. That is so that's I was thinking yesterday when we had something that see now think about how it's he will be added here because he is CL will go here because he wants to put CL.
Okay, while people are still doing that, so it's October the 1st, and we finished chapter 18. So what's going to happen Friday, Monday, and Wednesday, I'm going to be in here at normal time for office hours. So you can come and we can chat about stuff and you can do practice and such, but there's not going to be an actual lecture. We're a week ahead. So. What?
So there were 4 weeks behind, no Chem 1, 2.
Yes.
Would it be this? 1503 and H2SO.
Nitrate first. For that, you want to do a Friedel-Crafts acylation.
Okay.
Yeah. Okay, so show of hands, who voted to do the chlorine first? Nobody likes chlorine. You like chlorine. Okay. So everybody else did the nitrogen group first?
Yeah.
Oh, okay. So I'll do it the other way. Okay. So if we do Cl2 with AlCl3, oh, that's probably because y'all forgot that you could do this chlorination like this. You can do this. All right, so that puts on our chlorine. And then we don't have a way to get the NH2 directly. We have to do it indirectly through the nitro group, so we have to do a nitration. And fortunately, halogens are deactivating groups, but they're ortho-para-directors. So, I mean, we'll get some substitution at the ortho position, but we can ignore that because presumably between each step we're doing a workup procedure and we isolate the stuff and all that. And then all we have to do is reduce the nitro group. So zinc and hydrochloric acid, and then sodium hydroxide. Bam. Okay, let's do D and then we'll be done. Oh my God, there's 3 groups.
Yeah.
So look at each group's relation to each other group. So the chlorine is an ortho-para director. So it has things that are ortho and para to it. So that would be a potential good candidate for the first thing to attach. The nitro group has something meta to it and something ortho to it. So it could go on, at some point, not at the end. And then the acyl group is also a meta director. So the chlorine's probably going to be your best bet. Or think about it this way. If you install, what you could do is install those 2 groups because they're meta to each other and they're both meta directors. So you could do the acylation first, then it would direct meta, so you could add the nitro group. Or you could nitrate first, and then you have a meta director, then you can add the acyl group. Now, these are both meta directors. That's the meta position, so you're screwed.
No, I think that's what I was thinking. No, please. I know, and then like. It's always when I go knowledge that I have in this. That's okay. As you like the mentor is something I saw that I was like I and it's like you can't do that. No, you're just but there's enough.
Okay, votes. Nitro group or acyl group first? Interesting. Okay. It's a neutral interesting. If you were actually doing this reaction in the lab, doing a nitration on a group that has, on a molecule that has a lot of stuff on it could be kind of dangerous. You might just tear your molecule apart, but don't worry about that. Okay, so that's an ortho-para-director, and so when you have an ortho-para-director, you can assume that it's going to react in the position that you want it to react in, because you will actually get both. Okay, and then nitro group. One advantage of doing it this way is here you've got, right, this is the group we're aiming for. The chlorine is an orthodirector, and the acyl group is a metadirector. So we've got multiple things both pushing the nitro group to go to that position. You could do it the other way, where you start from, do the chlorination first. Do the nitration. That's ortho, so that's valid. Acylation, para-directing, and meta-directing. And so again, we have both things directing to that position that we want. Nice. Any questions?
So we can do it both ways on the paper, but if we were doing it in the lab, would the compound would be the way when you're supposed to do it?
Probably, I don't know. You could either one would probably work. Actually, the top one would give you better selectivity for this position in the final reaction. But don't worry about that.